Okay, chapter 22, Introduction to Alpha Carbon Chemistry. Now I'm going to say we're getting into some weird stuff. All right? So what we've had up to this point, we've seen this carbonyl-carbon now for 3 chapters. I promised you we would have 3 chapters of chemistry. That was chapter 19, chapter 20, and chapter 21. Wow. 3 chapters of chemistry right there at that moiety. So, wow. Now we're going to have more on this in chapter 21, in chapter 22 and 23, but it's weird stuff. All right. So hopefully you're comfortable with the stuff we've done up to this point. So for carbonyl compounds, let me tell you a little bit about this first of all. Greek letters are often used to describe the proximity of atoms to the carbonyl center. In other words, how close they are, right? That's what proximity means. So the alpha carbon is 1 carbon away from the carbonyl carbon. The beta is 2 carbons away. The gamma is 3 carbons away. So this chapter, I think, is entirely dedicated to that carbon and this carbon, the alpha carbons. Okay? Yeah, that's what it says here, right? This chapter will primarily explore reactions that take place at the alpha carbon. All right, so the reactions that we're going to look at are going to proceed through either an enol intermediate or an enolate intermediate. So you've seen an enol before. We saw this in chapter 8 or 9. An enol has, look at that. You see, where's my marker? Lost my marker. Here it is. We see an ene, right? All. So this is an enol, okay? And this is an enolate because 8 is something that we've seen, and when we see 8, what we know is we have an anion with oxygen in it, right? All the 8s that we've seen up to this point, I think all of them have had an anion with an oxygen in it. And so that's where the enolate comes from. That's an enolate, that's an enol. Can you see that this simply is just, this is the conjugate acid of this base, or that is the conjugate base of this acid? Right. So the reactions that we're going to look at in this chapter go through an enol or an enolate intermediate. Now, in order to get that, we're going to either use a trace amounts of acid or base, or we're going to use a strong base, right? So that's how we're going to get them. We'll look at the mechanisms for it in a little bit, and this is a sort of a sneak preview of what we're expecting to see at the alpha carbon. We're expecting to basically put something there at the alpha carbon. Okay, as I said, trace amounts of acid or base provide equilibria in which both the enol and the keto forms are present, right? So if we use a very small amount of acid or base, we're going to have significant amount of enol and a significant amount of the keto. Do you remember what this is called? We called this enol, keto, enol, tautomerization. These are tautomers. These are tautomers of each other. They are not resonance contributors. What's the difference? Good question. I'm not, I think, organized enough to promise that you'll get this on a quiz, but boy, is that a good quiz question. How are they different? I will tell you, even if I don't have it on the quiz, it would benefit you to stop and think about that and to generate some answer. It'll help you get deeper or have these concepts settle more firmly in your mind. All right, it is an equilibrium. Yes, yes. It is not a resonance. No, no. And there's an equilibrium arrow. That's how you know. All right. Well, there's another reason that you know, and that's when you look at the difference between these two. You'll see by looking at the structures, you can tell it cannot be resonance. Okay. At equilibrium, typically greater than 99% of the molecules exist in the keto form. Keto, keto, keto. All right? Greater than 99% at equilibrium, typically, depending on the structure, of course. Why is that? Again, another thing that will help you, if you can think about that in your mind, maybe even write a note out about that. It'd be a great way to settle that concept in your mind. If you don't know the answer, bring it to class. Bring the question to class. All right, in rare cases, such as the equilibrium example below, the enol form is favored. Why is that? Look at this. Give two reasons. 1, 2. And 2 reasons why, in rare cases, 70 to 90% of this ketone is going to exist as the enol. Right? You see that? Ketone and enol. Wow. The majority of it, 70 to 90%, exists as the enol. Why? And another point is the solvent can affect these exact percentages, but that is not one of the 2 reasons given. They're super common answers. I've asked this question, honestly, hundreds of times. Well, scores of times in class, maybe hundreds. Okay, now phenol is an example where the enol is vastly favored over the keto at equilibrium. Why is that? What do you see about this structure that tells you it's going to be more stable? And I'm going to get a different color pen here in case you're tempted to go to sleep right now. Much more stable. Why? 2 reasons. The same 2 reasons as previous slide, I think. Okay, so phenol is another example where the ene, see that? All, where the enol form is going to predominate. All right, and you can see it is a dramatic difference between the 2. All right, now the mechanism for tautomerization depends on whether it's acid or base catalyzed, as you would expect. All right, so let's walk through. Let me get a different color pen. I don't think you need my help here at this point, but many of you are really good at this. But let's walk through it. If I have an acid catalyst here, then I'm going to first of all protonate this. You've seen this structure hundreds of times, I'm sure of it. And this is now going to be resonance stabilized with the movement of electrons, not the movement of nuclei, just the movement of electrons, right? And can you see that if I move these electrons up here, boom, then I go back to my sp3, or I go back to my neutral oxygen, which is now sp3 hybridized, and I have my carbocation is shared, right? The real structure looks like this. Does that sound like a teenager making macaroni and cheese? Kind of does, doesn't it? In the background, do you hear the background noise? Okay, he's almost not a teenager, but it still sounds like a teenager making macaroni and cheese. All right, now I drew this wrong, right? Because they're not a positive here and a positive there. It's really a partial positive. I was distracted. And there's a partial positive here. That's the real structure, right? That is defined by these 2 resonance contributors. Resonance contributor 1 and resonance contributor 2. Here's the resonance hybrid. Hopefully this is all terminology which is old friend to you by now. Okay, so again, looking for how we're going to get the tautomerization, we first of all protonate this. Boom, there's step 1. We protonate that. Of course, these electrons leave off and make your water molecule. Then the water molecule comes back in and takes that proton. And these electrons come over here, bam. And there you go. All right, so here's your enol. Here's your keto form. Draw that out. I don't think exam 3 can be well written without giving you points for knowing this. It's true. It's going to be in, I think it has to be in there somewhere. I should stop short of promising, but this is so central to this whole chapter. So this is if it's a acid catalyzed tautomerization. This is acid catalyzed tautomerization. I'm guessing the next slide, I don't have these memorized, but I'm guessing next slide is base catalyzed tautomerization. Of course, right? Exactly what you would have expected. Now, if it's a base catalyzed tautomerization, then I've got, oh, let me go back a slide. Look at this here. Do you see that you have a hydrogen on here, right? I'm going to go back and forth. Now let me go back to slide 8 for a second. You see there's the hydrogen. I'm going to go back to slide 7. There's the hydrogen there, right? But it's not drawn out. I know you know why. The vast majority of you know why, but please don't forget that it's there. The reason I take video time to accentuate that is because I still see those mistakes on exams. Late into Organic 2, and it's still possible. Some of you maybe have not trained your eyes well enough to know that. And occasionally I'll see 5 bonds on a carbon, or 6, or 4, or 3, or less. And so it's you got to get used to that. So let's go back to the base, slide 8, next slide, and we see here that in a base catalyzed tautomerization, the base is going to take that hydrogen, which that's a carbon-hydrogen bond. You typically would not expect that to be acidic, right? Do you remember that the pKa of this guy right here, this hydrogen, is about 50? What? 50? You don't expect that to be deprotonated. Aha! But it's right next to a carbonyl carbon. That's what this whole chapter is about. This is bizarre. Look at this. So we get a hydroxide, which can come along and take that proton. If it does, these electrons are left there. Do you see they make the carbanion, which is very ugly? Very, very ugly. You do not like that. But it is resonance stabilized, and that's the whole reason why this can exist. Okay? This is center stage. Now, I should ask you, please draw the resonance hybrid. Pause the video here and draw the resonance hybrid. Okay, I'm going to suppose that you did. I'm going to draw the resonance hybrid here. That will give you the positive feedback. They both have carbon, 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 right? So I'll draw that. They both have a carbon-oxygen bond, right? I'll draw that. They both have at least 2 lone pairs of electrons. I'll draw that. One of them has a minus on it. One's neutral. So this is going to be partial minus up here, right? One of them has a double bond here. Oh, one has a double bond right here, and one has a single bond right here. So that's going to be a partial double, right? And look at this over here. One of these has a double bond, and one has a single bond and a double bond. So this is going to be a partial double, right? And then one's got a neutral, or rather -1, and a neutral over here, partial minus. This looks a lot like carbonate, right? Or acetate. As practice, write out the full Lewis structure of acetate and convince yourself this looks a lot the same. What you know, what you learned about that, you can apply to what we have here. Okay? So again, base catalyzed tautomerization, base comes in, boom, takes proton, proton leaves electrons behind, same old story, of course, always, and you're left with a carbanion. The carbanion is resonance stabilized by these electrons. Whoops, whoa, sorry. These electrons come here, these electrons go up here, and boom. Okay, there's your other resonance contributor. Now, this oxygen takes a proton from water, right? And that goes back here. And you're left with hydroxide, by the way. And that's what you started out with, right? This is a catalyst. So you're expecting it to be there when you're done. And now we've got our, watch this, enol and our keto. Okay, so that's base catalyzed tautomerization. We've got a long ways to go. Let me move on. Okay, now, as the tautomer, I'm going to go back to a different marker. Can I go back to red? Okay. As the tautomerization is practically unavoidable, some fraction of the molecules will exist in the enol form. Okay? Tautomerization, so in other words, if you've got acetone, it's not acetone anymore, it's a protonated, this is the enol form, right? That's enol. But if you have acetone, you're going to have some, you see that's the keto form is right here. And we know the name of that is acetone. This is going to exist. If you have acetone, since tautomerization is practically unavoidable, you're going to have some of the enol around. All right, now let's look at the enol form. We see that there is a minor but significant resonance contributor where the negative charge is, wow, on the carbon? Are you serious? What? We have a separation of charge here. And a positive charge on electronegative element. And a negative charge on electropositive element. You might want to listen to this slide again, okay? Because this is really important and it's a little subtle. You have a negative charge on electropositive element, which is what? Carbon, right? So you don't like this structure. No, bad, 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 bad. Yes, you do like this structure. However, even though this is substantially more stable, so you would expect the hybrid to look a lot more like this, still, there is some of this around. In other words, it is a minor but significant resonance contributor with a nucleophilic carbon atom. Nucleophilic carbon atom right there. Now, go practice with conceptual checkpoints 22.1 through 22.3 and come back. We're not done with this video. Pause it now and do those checkpoints. Okay, now I'm going to suppose that you did those. In the presence of a strong base, now here's the other possibility, right? We were talking about weak bases before, or rather trace amounts of acid or base. In the presence of a strong base, an enolate forms. What's that? Well, we looked at the structure of enolate a few slides ago, but let's look at it more carefully. Suppose you have a strong base here. It comes and takes this proton. That's the alpha proton. Remember that, right? This is the alpha carbon. This is the alpha carbon. In this case, this is just acetone, so it's symmetric. So this hydrogen is the same as all the other hydrogens on here. The alpha proton can be abstracted with a strong base. If it's abstracted with a strong base, then we're left with a carbanion, which is resonance stabilized. This is the enolate. Enolate. Oops. Enolate. Have you noticed how smoothly I'm using all these big words? It's the middle of a day, it's beautiful sunshine outside, and I'm not tired. Usually I'm tongue-tied, and I have to call everything the thing. But today, I'm calling enolates, and I'm saying resonance stabilize. I'm unusually clear today. I should do all my videos today, Saturday, middle of the afternoon. All right. So again, sorry for the sidetrack. I was just all right. I have a base here. Base comes. This is a strong base now. Comes and abstracts a proton. If it abstracts the proton, then we're left with the carbanion, which we saw on a previous slide, and the carbanion, the electrons come here, make a double bond, push those electrons up, and you're resonance stabilized by like such. Okay, which of these two, structure 1 or structure 2, which is better? Which is more stable? Structure 1 or structure 2? Structure 2 is more stable, right? Because I have my negative charge on the electronegative element. Wow. Oops. Oh, come back. Right. So now the enolate is much more nucleophilic than the enol. Why? That's a good question. The enolate is much more nucleophilic than the enol. Why? Okay, let's move on. The enolate can undergo a carbon attack or an oxygen attack. Really I don't like the word undergo. I'm going to say effect. It can affect an attack by an oxygen or by a carbon, right? They generally affect carbon attacks. Why is that? Why? Bring that question to class. Enolates generally, for now you could memorize it. If you don't understand that, I would say it's going to be so common you might just want to memorize it. That we're going to see that we're getting chemistry, we're getting a reaction at the alpha carbon. Right? Okay, so we're generally going to see that the carbon does the attacking. All right? Now, let's probe what's going on here even a little bit more. Alpha protons are the only protons of an aldehyde or ketone that can be removed. They're the only, let me say this again, they're the only protons on an aldehyde or ketone that can be removed to form an enolate. Why? Well, draw the structure. If that's not obvious to you, please, I beg of you, pause the video, draw the structure, prove it to yourself, because it's a big deal here. Turns out removing the aldehyde proton or the aldehydic proton or the beta or the gamma proton will not yield resonance stabilization. And so it's not going to happen, right? Then you're back up to pKa's of 50 or such. Okay? Go practice with Skill Builder 22.1. Practice with Skill Builder 22.1 and come back. Okay, I'm going to suppose that you did. We've got a little ways to go here. Actually, a long ways to go. This is a long video. So now draw all possible enolates that could form from the following molecule. Now, in order to do that, draw all possible enolates. I'm going to pause the video now, and then I'm going to make some comments about it when we come back. Okay, I'm going to suppose that you paused the video, and I'm going to take one small fact, which hopefully you heard. Enolates are going to come from the alpha hydrogen. So the first thing I'm going to do to make this easy for myself is I'm going to go through and draw all the alpha hydrogens. Right? There's an alpha hydrogen. Well, there's two more here, but I'm only going to draw that one. Okay, how many hydrogens are on this carbon? None. Right? Okay, let's look over at the other carbonyl. There's the other one. Where's another alpha carbon? Well, that's not an alpha carbon. That's an oxygen, right? Here's an alpha carbon. So here's another one. Agreed? Okay. So let me say that that is a hint about what can be done here. All right. Okay. So I'm not going to draw all these enolates out, but bring them to class. It's great practice. All right, so why would a chemist want to form an enolate? Well, we've got a hint, at the beginning of the chapter. You already got a hint for this. Right now, I think it's not unlikely that some of you are just sort of being dragged along and haven't really appreciated that yet. Why would a chemist want to form an enolate? Well, there's a reason. And you know what? I'm not going to tell you the reason, but please think about that. Okay. So now, to form an enolate, a base must be used to remove the alpha protons. To form an enolate, a base must be used, right? So in the base catalyzed version of it, it was hydroxide. In the acid catalyzed version of it, the base was water, and in the strong base catalyzed version of it, we just called it a base, right? That's all we called it. Now, the appropriate base depends on how acidic the alpha carbons are, of course. If you're going to take that proton off of there, you have to have a base that can do it, right? We got that in chapter 3 of Klein, and we also got that in Gen Chem 2. Yeah, you can't, if you're going to take a proton off, you got to have somebody who's strong enough to do it, right? Now, on the other hand, you might not want to drop a nuclear bomb on this guy. So you might want to get a base that is just strong enough, but not strong enough to deprotonate everything else. And so that's what the next couple slides are dedicated to. Hopefully this will appeal to some things that you learned in previous courses and previous parts of this course. So the appropriate base depends on how acidic the alpha protons are. What method do we have to quantify how acidic something is? We've done this several times now. No, more than that. pKa, right? It's pKa tables, really. And the question here is method. I should say, how do we quantify? Well, we look it up in a table, right? A pKa table. And the pKa table is just a bunch of structures and numbers, but it's hugely powerful. It tells us tons of information. All right? So let's compare some pKa values for some alpha protons. So you have acetone. It has a pKa of 19.2, and we know that because we looked it up, right? That's not something that you're expected to know. But look at that. Look at it. What does it mean? So the alpha proton of acetone is 19.2. Okay? And after it's subtracted, its enolate looks like this, right? And this is resonance stabilized. Now, the alpha hydrogen, the alpha proton of acetophenone is 18.3, right? Why is that? That is so weird. It's 10 times more acidic. Why is that? It's 10 times more acidic. All right, look at that. Tell me why. All right, now, acetaldehyde, on the other hand, is more acidic yet. Look at that. It's more acidic yet. This is 1,000 times more acidic. Like that. Well, not 1,000. Almost. Acetone was 19.3. Acetophenone was 18.2. This is over 100 times. It's maybe like 500 times more. Okay? Because it's a P scale, right? So 19, 18, that's 10 times more. Drop it really almost 2 more, okay? To 16.7, this is much more acidic. Why is that? Okay, now remember, and I'm not going to tell you why, but look at it. This is review. Bring it to class if you don't know. Please ask me out in class. Now, when pKa values are similar, both products and reactants are present in significant amounts. This is Gen Chem 2. So, we have a pKa of acetaldehyde of 16.7. We have a pKa of ethanol, look at that, of 15.9. So this is almost 10 times more acidic. That means it's mostly going to go that way, right? Because the stronger the acid, the more that it gets to act like an acid, right? There's many ways we could state that. We could do that with looking at the K of this reaction, right? The equilibrium constant of this reaction, or the pKa. Okay, now which side does the equilibrium favor? You can see by the arrow there. I already answered that. All right, so in this case, it's an advantage to have both enolate and aldehyde in solution so they can react with one another. What? What are you talking about? So they can react with one another. Pause the video now and make some notes about that statement right there. So they can react with one another. So they can react with one another. Okay? What does that mean? All right. Now, look at this. We have, in this case, an advantage to have both the enolate and the aldehyde in solution. So it's going to, the reaction's going to predominantly go this way because the pKa over here is smaller, right? That's the acid over here. This is the acid over here. This is the acid, right? So it's the pKa with the smaller acid that wins. So it's going to go this way because it's a smaller, it's the smaller pKa. Not sure if I said that correctly, but I think you get what I'm saying here. Now, show how the electrons might move in the reaction between the enolate and the aldehyde. Make a guess. Give you a hint. Chapter 19, Chapter 20, Chapter 21. That's the hint. I promise you'd see this over and over again. There's me delivering my promise. All right, now let's move on. If you want the carbonyl to act irreversibly, we can do that. Right? Why is this irreversible? If you want the carbonyl to be entirely enolate, oh, we can do that real easily. Put hydride in there, right? We typically do this as sodium hydride. Put hydride in there. You make hydrogen gas, and this bubbles out. Right? So it leaves. So we don't have I was doing so well with my vocabulary, wasn't I? We don't have an equilibrium. Yes, easy word. I just lost it. We don't have an equilibrium because one of your products bubbles out as a gas. We lose that product, and Le Chatelier's principle essentially drives the entire reaction that way. When is it synthetically desirable to convert all of the carbonyl into an enolate? When do we want that? I'll give you a hint. Have you paused the video if you want to guess? Okay, here's the hint. I'm going to go back a slide. Sometimes you want that, right? Okay, if you don't want that, then you're going to get that if you've got a bunch of the keto form in solution. All right, let's move on. Now, LDA is a stronger base. LDA, I think that this is lithium diisopropyl amine, LDA. When you write this on a quiz or exam, draw the structure out. If you want credit for that, draw it out. Full credit comes from drawing that structure out because it's so important. The structure of this tells us all of why this is going on, what's going on here, okay? So this is a very strong base, extremely strong base. Amines are strong bases, right? But this is probably diisopropylamide. It's probably amide, right? Because it's not an amine. You see that? It's a deprotonated amine. But an amine would be a base, but if I've deprotonated, it's even stronger base, right? So go look up the pKa of this. What would the pKa of this be? What would the pKa of that be? Look it up. You're gonna like it. It's gonna screen. Not pKa. Sorry, pKb. Well, the pKa of this is over here. Okay. I don't mean pKa. I mean pKb. Man, I was doing so well. My handwriting now is a mess. Okay. pKb. But really, let's just stick with pKa's for now. That's probably gonna be a simpler way to the same truth. Okay. So if you have this stronger base called LDA, you draw it out, 2 isopropyls on a nitrogen, that takes this proton. Why is this reaction effectively irreversible? This is like doing sodium hydride, right? But why is this effectively irreversible? Well, it's because we've got a pKa over here of 36, a pKa over here of, let me say 16 for the sake of the argument. It's what? 1 times 10 to the 20 more acidic. 1 times 10 to the 20. Wow. In other words, you're not going to have an equilibrium here. Okay? Now, LDA features 2 bulky isopropyl groups. Why would such a bulky base be desirable? What are we trying to avoid? It's really, really important. I'll give you a hint. Chapter 19, Chapter 20, Chapter 21. Right? We have a nucleophile here. Now, it's really not a nucleophile because it's so big, right? Okay, that's way more than a hint. Please work that out in your head. If you've budgeted enough time for this and you have the spirit for it, I suggest you actually draw out the reaction. Okay? Make some notes on that. All right, when a proton is alpha to 2 carbonyl groups, its acidity is increased. And I'm going to put another word in here. Watch this. This is, you would say, of course, watch this. Substantially increased. It is substantially increased. Of course, right? You knew that if you had a carbon like that, the pKa of this, in general, if it's sp3 hybridized, you're expecting the pKa to be about 50, between 40 and 50, right? Well, if we put a carbonyl carbon, look at this. If we put a carbonyl carbon here, it drops to what? 17? Wow. I mean, please let that sink in. This is log scale, right? In other words, this of acetaldehyde. Acetaldehyde is about as likely to give up a hydrogen as water is. That's unbelievable. That's just unbelievable. All right. That said, what would a second, if I put a second, where am I here? Where's my marker? Let's put a second carbonyl carbon on there, which I do here with this guy, right? Look at that. You would expect it to drop even more, and it does. Okay? Now all of a sudden, this is an acid, right? Because its pKa is much less than water. It's more than 1,000,000 times more acidic than water. Okay, so draw all the resonance contributors that allow 2,4-pentadione to be so acidic. Draw those out. This will really help this concept sink in. Draw out all the resonance contributors that allow 2,4-pentadione to be so acidic. Okay, 2,4-pentadione is acidic enough that hydroxide or alkoxides can deprotonate it irreversibly, as you would expect. Just exactly what we were saying a second ago, right? The pKa over here, whoops, whoa, just a second here. The pKa, just a minute here, over here is 9. It's 16 over here. It's 10 million times more acidic. In other words, so, right, if it was the same, we would draw it like that, right? If this was more acidic, we would draw it like that. But if it's 10 million times more acidic, we simply say, all right, you're not going to get an equilibrium here. It's going to be irreversible. Figure 22.2 summarizes the relevant factors that you need to consider when choosing a base. You go practice with conceptual checkpoints 22.6 and all the way through 8. And I think that's it for this video. Best wishes.